In this video, we will talk about the comparison tests for series. We have seen comparison tests for integrals. Now we will have something similar for series. Um, Typically in these tests, you will determine the convergence of your series. I mean, the series may not look nice. You will try to compare it with something that you know. Most of the times, we use geometric series to compare and p-series because these are simple, they're easy, and more very common. So let's consider the following example first. I have the series sum from n equal 1 to infinity of 1 over n squared plus 1. If you want to see, I mean, which does it look like a familiar series? Well, you may see that it's not very far from sum from n equal 1 to infinity of 1 over n squared. Moreover, there's something really nice that I know here, that 1 over n squared plus 1 is less than 1 over n squared, and both of them are positive. Okay, so that means that if I take the nth partial sum, so from k equal 1 to n of 1 over k squared plus 1, this is going to be smaller than the nth partial sum of 1 over k squared from k equal 1 to n. Okay, which is smaller than the sum if I'd let this go to infinity. So I know that this is what? Convergent. That's a p-series. And because this is convergent, so of course it's gonna go to a finite number. So then that sequence Sn is less than a number, so it's bounded above and it's bounded below because of the 0. I know it's also increasing. We have seen this before because every time you are adding positive terms. Okay, so by the monotone convergence theorem, that's going to be a convergent series, which means sum from n equal 1 to infinity, 1 over n squared plus 1 converges. Now, no need to keep saying that by the monotonic convergence theorem, and this is less than this and it's increasing, because from now on, we're going to just call this the comparison test. Okay, so it's very simple. Suppose that, and after some integer n, you have the following behavior. So it's not necessarily that you're going to have an less than bn from the beginning. Maybe they will alternate, or maybe an is going to be bigger than bn for the first 100 terms, but then things will turn around. So let's say after some number n, okay, capital N, I got this inequality. Always here, till now, all the series that we are considering, other than the geometric series and the telescoping, these were special cases. But when we were talking about the integral test and in this section, we are only considering positive terms. You will never see negative terms in this video. Okay, so we start talking about negative terms when we talk about the alternating series later on. So an is positive, an is less than bn. Now if the sum of the big one, if the sum of bn converges, then I can conclude automatically that the sum of an converges. Now if it diverges, it doesn't tell me anything. So if the sum of bn diverges, well, the sum of an is smaller, it could be infinity also, it could be some number, so it's inconclusive. However, if you know that bn is less than an, okay, you see here the inequality is different. If you know here that the sum of bn is divergent, then because an is going to be bigger than bn, so the sum of the ans will be bigger than the sum of the bn's, then it's going to be divergent. Here's an example. Suppose, so the idea here is to try, so if you have an, the idea is you need to find bn. You need to find bn so that it's bigger or less. It depends on how it looks like. From the experience and practice, you will be able to tell. So for example, here I have this. So this is my A sub n. I want to compare it. I want to use the comparison test to see whether it's convergent or divergent. Okay, so why don't we choose Bn to be 1 over n squared? Notice something, that 1 over n squared plus 3n plus 1. Remember here that n takes values from 1 to infinity, so n is always positive. So this is some positive quantity. So you are making the denominator bigger, so the fraction becomes smaller. So this is smaller than this. That means that an, we can put smaller or equal, is smaller or equal to bn. But the sum of bn converges because it's a p-series. Do you see how useful the p-series are now? So that's a p-series. I know it's convergent. So by the comparison test, I can conclude that the summation of an is convergent. Okay. So very interesting. Another example, you can see that this is different. You don't have n squared, you have an exponential. Okay, again, this is your an. You want to compare it to some function bn. Now you should have the feeling that this is going to be convergent, because you know in the denominator you have exponential. This is growing too fast, so the denominator is getting bigger too fast. So that means it's going to approach 0 faster. Compare it to bn equal 1 over 2 to the n. Do you see how I can relate it to that? Like, for example, over there, I compare it to just the leading term. That's the same idea here. Again, it's kind of simple because it's the same idea as the previous one, 2 to the power n plus 1. I know this is less than 1 over 2 to the power n because the denominator here is bigger than the denominator here. And this is a geometric series. This is the same as 1/2 to the power n from n equal 1 to infinity. So this is geometric. It's convergent as it's a geometric series with ratio r between -1 and 1. R is 1/2. So by the comparison test, the series sum from n equal 1 to infinity, 1 over 2 to the n plus 1 is going to be convergent as well. Okay, I mean, so far things are really easy when I'm comparing. But what if I have something like that? Now again, here I have the feeling that this, okay, so this is an, I have the feeling that this must be compared to bn equal 1 over n squared. But I can't really do the same thing I did earlier. Why? Because 1 over n squared minus 1 is not less than 1 over n squared. This is not true. Okay, so this is not true. Actually, this is bigger. Okay, but if it's bigger, it doesn't mean it's going to be divergent. Something bigger than convergent doesn't mean divergent. We can do some algebra here and try to show this, but I'm going to give you a stronger tool that will work for some other series. So I'm going to get back to this example. Before, I want to talk about the limit comparison test. I have talked about something similar for p integrals. Okay, so here's the idea. This is stronger than the comparison test. Again, you can only use the comparison test, you can only use the limit comparison test if the terms are positive. So suppose that I have an, bn greater or equal to 0 positive sequences. Now, assume that I'm finding the limit from n goes to infinity of an over bn. If the limit of this ratio is some number L not equal to 0, then the two series are the same. Either both will converge or both will diverge. If the limit of the ratio is equal to 0 and the one in the denominator converse, then the series converse. If limit when n goes to infinity of a over bn is infinity, and the denominator, the sum of the sequence corresponding to the denominator diverge, then sum from n equal 1 to infinity of an diverges. Okay. Now, if you got 0, for example, in the second case, and the summation from n equal 1 to infinity of bn diverges, doesn't tell you anything. The same thing here. Okay, so I have this listed as a remark. So before going to there, let's try now to do this problem. So this is an. I'm going to compare it to bn equal 1 over n squared, but I'm not going to use the comparison test. I'm going to use the limit comparison test. So let's see here what we do. We're going to take the limit of an over bn. If it's equal to L, then the two series will be the same. So let's find this limit of a sub n over b sub n when n goes to infinity. This is the limit of 1 over n squared minus 1 over 1 over n squared. So this is the limit when n goes to infinity. Over here you're going to have 1 over n squared minus 1 divided by 1 over n squared means multiplied by n squared over 1. So that's the limit when n goes to infinity, n squared over n squared minus 1, that's equal to 1, which is not 0. So this corresponds to the first situation in the theorem. That means summation, since I know that summation of bn is convergent as it's a p-series, so then you can conclude that summation of an from n equal 1 to infinity converges, meaning that this is convergent. So again, this belongs to this situation where I found that L is equal to 1. Okay, so here what I was talking about. So if you find out that the limit of n over bn when n approaches infinity is 0, and the sum of the denominator is divergent, then the limit comparison test is inconclusive, gives you no information. Okay, same thing if an over bn is infinity and this is a convergent, I know that when it's divergent then an is diverse, but here it's convergent, then also the test is inconclusive. Okay. Let's take a look at some examples. For example, here the direct comparison test doesn't work here because you have to think of comparing this to 1 over root n. Okay. And we know that summation of 1 over root n, which is summation of 1 over n to the power 0.5 or 1/2, you know that this is, as a p-series, this is divergent. So you want to make this bigger than this, but actually this is less than this. And I'm talking about this and this. 1 over radical n plus 1 is less than 1 over radical n. Okay, so what do we do in this case? We can use the limit comparison test. Okay, so this is an and this is bn. So I take the limit of an. It doesn't matter if you put bn in the top, if you switch the roles, it doesn't matter. Okay, so that's the limit when n goes to infinity. An is 1 over radical n plus 1, like that. And divided by bn, divided by this means multiplied by radical n. So that's the limit when n goes to infinity, radical n over radical n plus 1. Since I have the same order on the top and on the bottom, then if you want, I can just show you this. Limit when n goes to infinity, factor root n from the bottom, you get root n 1 plus 1 over root n. This cancel out, so that's limit when n goes to infinity, 1 over 1 plus 1 over root n. This is equal 1 over 1 plus 0, which is 1. When n goes to infinity, this guy goes to 0. So this means what? Since the limit of an over bn is equal to a number 1, which is not 0, that means that summation of an and summation of bn are the same. And because I know that the summation of Bn from here is divergent as it's a p-series with p less than 1, then I can conclude that summation from n equal 1 to infinity 1 over radical n plus 1 is divergent as well. Okay. Here's another example. Actually, this is no need for comparison test here. But if you want to compare it, you will compare it to 2 over 3 to the power n. Okay, you can try that, but there's no need because you can split this as a two series and they're going to be both geometric with ratio less than 1. But if you want to use the limit comparison test, you can try this, choose Bn to be 2 over 3 to the power n and compare. That one, again, if I want to compare it, so this is my An. Okay, I look at the numerator. I see it just like it's like it's similar to a polynomial. So I have like a rational function here. The degree of the top is 2. The degree of the bottom is 4. So I'm gonna choose Bn to be 1 over xn squared. Okay, and it's gonna work. You will be able to see that limit of An over Bn when n goes to infinity. In this case, it's gonna be 1. Because this guy is convergent, so sum of Bn converge because it's a p series. So then my series will automatically converge. Sometimes things becomes a bit more challenging, like this example. You want to compare, you want to use the limit comparison test to do this. Actually, let's see. The integral test can be applied, but this is not a well, yeah, it can be done here. I mean, the integral can be done by integration by parts. It's not too bad. But let's try to do it using the limit comparison test, as it's easier in this case. But again, as I said, it's a bit tricky. Here's why. If you try to compare it, maybe you will say, okay, I'm going to compare it with Bn over 1 over n squared. If you do that, you're going to get limit when n goes to infinity, An over Bn, so ln of n over n squared. You're going to get ln of n, which is infinity. Okay, so you know that this is convergent. Okay, and you get the limit equal to infinity, but in this case, the test is inconclusive. You don't conclude anything. Suppose that, okay, so suppose that someone will lose the hope that this is convergent and will say, okay, you know what, I want to compare it to 1 over n. So limit when n goes to infinity, ln of n over n squared divided by 1 over n. So that's going to give me limit when n goes to infinity, ln of n over n, because one of these n's will cancel out. So then this is infinity over infinity. Apply L'Hopital's rule. You get limit when n goes to infinity, 1 over n divided by 1, which is 0. Okay, now the limit is 0, but the one in the bottom, which is Bn, is divergent. So also the test is inconclusive. Okay, so what do we do in this case? Now I want you to notice something. When I took Bn equal 1 over n, it went to 0. When I took it 1 over n squared, it went to infinity. So my guess would be Bn equal 1 over n to the power something between 1 and 2. I mean, not between 1 and 2. I mean, something like, yes, 0.5, for example. Okay. So let's see what happens in this case. So I'm trying to choose something less than 1 over n. Because at 1 over n, it was inconclusive. If this doesn't work, maybe I choose something like 1.5. So limit when n goes to infinity of ln of n divided by n squared, so this is an, divided by bn, which is 1 over n to the power 0.5. This is equal to limit when n goes to infinity ln of n over n squared times n to the power 0.5, which is limit when n goes to infinity ln of n over n to the power 1.5. Now take the derivative, okay, the L'Hopital's rule. So this is going to be the limit when n goes to infinity 1 over n divided by 1.5 n to the power 0.5. 1.5 minus 1. So this is equal to 1 over 1.5 n to the power 1.5. So this goes to infinity. This goes to 0 when n goes to infinity. So this is not helpful, okay, because this is giving me the same result as bn equal 1 over n gave me. Okay. So what I do here, maybe I'll try something else. I'll try bn equal 1.5 and see what's going to happen. So if this is the case, then let's see. So this is going to be some, I'm going to change all these. So this is how you can sometimes compare. If you want to use the comparison test, it might be a bit challenging. So in this case, if the test is inconclusive at one point, and so you can try like something in between, especially if you are using p-test. So you can try something below the 1 or something above the 1. So I'm going to try now n to the power 1.5 and see if this is going to work. So now I take the limit when n goes to infinity ln of n over n squared over n to the power 1.5. Over 1 over n to the power 1.5. So that's the limit when n goes to infinity ln of n over n squared multiplied by n to the power 1.5. So that's limit when n goes to infinity ln of n over n to the power 0.5. Now when n goes to infinity, what happens is that this is going to be limit of infinity over infinity. So I apply L'Hopital's rule. I get the limit when n goes to infinity. ln of n is 1 over n. And this is 0.5 times n to the power negative 0.5. So this is the limit when n goes to infinity. 1 over 0.5 times n to the power 0.5. This 0.5 comes from adding this with this. And this guy goes to 0 when n goes to infinity. Okay, so now by the limit comparison test, if the limit is equal to 0 and the one in the bottom is convergent, then the series will converge. And I know that this is convergent as it's a p series, p is equal to 1.5. So then the original series is convergent. Okay. So this is one of the most challenging stuff that you can see here. Okay. I will select more example for you so you can try them out. It's rare to see examples of this form, but in case you see one, you saw how I was trying to do that. Okay, so I intentionally had to choose 1 over n squared and 1 over n at the beginning to show you that it doesn't work, and then I was trying to see what happens if I choose something below 1 over n, what happens if I choose something above 1 over n, because 1 over n is like the edge between the convergence and the divergence in that case.